Alright, what's up everybody? This is Ian. I'm covered. Today we're over here in the Learning Glass studio at SDSU. Big shout out to Patrick at the Digital Humanities Center for letting us use this room. So, today's problem is covering the topics of fluids mechanics. So, water flows steadily into the Y junction shown at point 1 with a velocity of 18 meters per second and a gauge pressure of 300 kilopascals. We have the area of section 1, and then it enters at section 2 and section 3. We have the area of section 2 as 6 centimeters cubed squared, and area 3, 10 centimeters squared. We also have that this one is going 50 degrees above the horizontal, and the third one is 35 degrees below the horizontal. If gravitational and viscous effects are negligible, find the force required to keep the system stationary. Okay, so one big thing when we first look at this is that we see that A1 is equal to the sum of A2 and A3, right? 16 is equal to 10 plus 6. And what that tells us is that because our total area inlet is equal to the total area outlet, we have uniform velocity throughout the system. We also know that there's steady flow. So when we look at the Reynolds transport theorem equation, we can cancel out the first part of the equation. And that first part is just the time rate of change of our variable velocity. And since we have steady flow, this is just negligible. So we're only looking at the second part of Reynolds transportation theorem, which is the net flow rate of velocity across our control surface. So let's get into it. For the x direction, we're going to have three different setups of our rho, density, times velocity, times the cross product of velocity and normal direction. So every time you have normal direction, you just know that that's the normal is facing away from the area. And this part of the equation is just looking at the relationship between your velocity and your normal. So here, since these are opposite directions, it's going to be a negative relation. And for the other two, it's going to be positive. You'll see what I mean when I write it all out. So for the first one, the first control surface, number 1, we have rho, and then our sign of our velocity, we're just looking at the velocity now, so the first arrow is positive. Oh, you can't really see. Okay, this is number 1 here. So just the velocity right now is positive. So we have plus v. And now we have that relationship of the cross product. So you can't see it here either, but I have my normal force going the opposite direction, normal. And this is the velocity. So since those are opposing signs, we're going to opposing directions, we're going to have a negative v dot n. Yeah, so that's just going to be negative v dot n, and then dA. And then for our second one, we have again, v is positive because it's going in the positive x direction, but then that dot product is going to be positive v dot n, dA2, I forgot my dA1. And then for the last one, again, same thing, positive, positive, and then positive v dot n, dA3. Okay, so after we integrate these things, the only thing that's has a relationship to time is velocity. And so we're going to be left with, for the first one, rho of v squared, negative, because of this negative here, so we can just put the negative out front. Negative v squared, and then dA1 just becomes a1. And then our second value will be rho positive, positive, v squared, a2. Oh, ooh, careful. That's not exactly in the x direction, right? Because it's an angle. So we have to get back to our basics of trigonometry. So our x direction is going to be cosine of 50. And then for our last one, it's density times v squared. And now cosine 35 of A3. Okay, and I guess I could just kind of make sure everything is clear here. Okay, so when we plug in these values, this is a water problem, so our density is going to be 1,000 for each case. So I'll write it out, 1,000. Density's unit is kilograms per meters cubed. And then our velocity, oh yeah, so remember we said that because the total area inlet is equal to the total exit outlet, the velocities are uniform throughout all cases. So our velocity is going to be 18 in every instance. So yeah, we have 18 squared, and then our area, 16 centimeters. If we convert that to meters, it's going to be 0.0016 meters squared plus 1,000 again. I'm going to start skipping on the units just to save time. Times 18 squared, area of 6, so we have 0.0006 meters squared, cosine 50. And then for the last one, again, we have 1,000 times 18 squared, cosine 35 of area 0.001 meter squared. All right, so if we sum those all up, we have negative 518 plus 124 plus 265. That's all going to give us approximately 128.1. And this is a force, so let's give it some newtons. Okay, so now we have that value for how the water is giving force in the x direction. So I'm going to put that over here. Okay, so now we're going to do the same thing, but for y. So let's just erase this. Again, we're using the Reynolds transport RTT. So the first thing for the control volume, the first portion of the equation is going to be negligible because we have steady flow. So again, we're just left with the density, velocity, and cross product between normal force and velocity. Okay. So for our first case, we're going in directly at the right, but in the y, that y is going to be 0. So, right, because it's only going in the x direction, so y is going to be 0. Okay, and now let's set up the rest of the equations for the second two. So we have rho, velocity is going up, so that's a positive velocity, right? So, and then the dot product again is positive, so we're going to have v squared a1. Oh, not a1, a2. And then remember the trigonometry, since we're going in the y direction, it's going to be sine of 50 now. Yeah. I should have moved out of the way. I guess you can't really see it that well with this yellow shirt and yellow marker. Okay, and then for the third one, now our sign is, we're going downwards, so we're going to have a negative. One negative from the direction of the velocity in the y direction. The cross product is still positive, so it's going to be negative when you multiply those. V squared a3 sine of 35. All right, so now we get those. We have 148 and 185, I think. I'm not sure if those values are correct. But this is going to give us Fy is equal to negative 36.9 newtons. Okay, so now we have Fy 36.9 newtons. Negative. Okay. So now that we did the Reynolds transport theorem, we have to answer what it's asking us for. Remember, what it was asking for was the force required to keep the system stationary. So if we have that force in the X and the force in the Y, do we have any other forces, class? Yes, good job, Jimmy. We have a force from the pressure and the area. Oh, another thing. 2 and 3 are open to atmospheric pressure, so that P value is going to be 0. This one is the only one that we are given a pressure for, which is 300 kilopascals. We have P and P1, A1. We have that right there. And that value is, I'm not sure exactly what that value is, but it's going to be 300,000 pascals times 0.0016 meters squared. So that is a force that we have in the X direction. So now we're just going to redraw our system as a free body diagram. So we have boop, 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 boop. We have P1, A1 here. And then we have, so if we have negative 128, we're going to flip it. So it's going to be in the other direction. We'll make it positive 128.1 in the X. And then we'll flip that 36.9 in the Y. And then so now we have these new variables, the hold variables that are going to hold the system stationary. So we're going to have Fx, Fy hold, and Fx hold. So we have the force from P1A1, we have our forces of the hold, and we have our forces. You always want to have the forces of the hold be opposite of these, and that's why I made these positive. I could have kept them negative, but I made them positive and going in the right direction. So it's like flipping it so that it's opposing the hold force. Because originally these were negative values, now I flipped them to make them positive so that they go against it. So now we just do our sum of forces in the X. We have P1A1. We have Fx hold. I'll just leave it at Fx. And we have 128.1. In the Y, we just have Fy hold and 36.9. Okay, if you solve these out, remember this P1A1 is just this right here. And so Fx hold is going to be equal to negative 608.1 newtons. And our Fy hold is equal to negative 36.9 newtons. So yeah, for this problem we use Reynolds transport theorem to solve for the forces acting in the X and Y direction of the fluid, which was water. And then we kept in mind that there was one force from the pressure in the area, that force there. And yeah, and then we solve for the hold forces because that's what's keeping the system stationary. These hold forces that we made up that are going opposing the direction of our water flow. So I hope that made sense to you guys. Thanks for watching and have a great day.